Hello, everybody, and welcome to day 2 of the 2021 summer series. Today, we've got one great workshop and one great panel for you today. The first, which is happening right now, is Drive Bases with Team Spyder 1622. And after our break at 5:50 p.m. Pacific, we will be having the Training a CAD Team panel with a bunch of members from our different presenting teams. So, without further ado, let's take it away, Team Spyder.
Hello, everyone. I'm Marshall Hammond, the systems engineer of our robotics team, and Micah, one of our mechanism leads, and I will be giving a presentation on common drive bases in FRC and offering some analysis on them.
So as Kyle mentioned, we're both from Team Spyder, and Team Spyder is going on to a 17th year in robotics, and we represent the Poway High School Engineering Academy. We build and program robots to compete in competitions like FOC, Vex, and FTC, but we also like to be part of a real business environment and get involved in a community from fairs to local government meetings. Our goal is to get involved with and help others get involved with STEM, which stands for Science, Technology, Engineering, and Mathematics. We travel to events around the world, connect to experts and professionals, and build sustainable relationships to make all of that happen.
All right, so kind of as a prelude to us talking about the different types of drive bases, let's make sure we have an understanding of the wheels that underlie the next few drive bases, which are non-holonomic wheels. Non-holonomic wheels are found everywhere from drive bases to flywheels and see use to their high traction. And as a result of this, and the resistance to motion is useful for the next few drive bases. The four most common non-holonomic wheels that you'll see in FRC are pneumatic wheels, which are inflatable, have high traction, and require occasional maintenance for punctures and rips. Must be replaced when the tracks wear out. Their size of 6 to 8 inches makes it so that they see use primarily in drive bases. Coulson wheels, which are smooth and require sparse maintenance and replacement. They have a wide variety of sizes. There are Versa wheels, which must be replaced frequently, have very strong grip, and come to 3 to 4 inch sizes. Finally, there are treaded traction wheels, not shown here. They're also treaded, require frequent maintenance, and have a diameter ranging from 4 to 8 inches.
So the first drive base we're going to cover today uses non-holonomic wheels, and it is tank drive, and it is the simplest and most common drive base you'll see in FOC. It's very simple to design, build, and program, and is the second lightest drive base we're going to cover today, except for Kiwi drive. The problem with tank drive is that standard implementations of it can have trouble toning since it uses non-holonomic wheels. It has a lot of ground contact and a lot of friction.
All right. This video will demonstrate an example of a tank drive base in action. As Michael was saying, standard implementations of tank drive may have trouble turning if they don't implement a center drop or wheels that have an easier time turning, such as Mechanism and Omni wheels. More detail about them later. This application makes it so that these can turn with ease. Tank drive offers pushing power, be it for traversing ramps, tough terrain, or moving and not being moved by other robots. And since it's extremely popular among teams, a lot of FRC games are designed so that a tank drive base will be competitive and useful in that game. Tank drive's minimalistic nature also leads to less points of failure and allows for teams to focus their time on the other mechanisms of their robot.
So as Marshall mentioned, one solution to tank drive's trouble turning can be to implement a center drop. And that's where West Coast comes in. West Coast is very similar to tank drive, but it does have a center drop so that the robot actually teeter-totters and it has less ground contact. Occasionally with West Coast and tank drive, one pair of wheels will be Omni wheels so that it has even less friction. And also, I should have said this earlier, but West Coast is built with 6 to 8 wheels instead of the 4 to 6 that tank drive is built with. Some benefits to West Coast drive are that it has very good pushing power like tank drive. It doesn't use very many motors, usually about 2 per side, and it is relatively easy to program.
In this video, you can see a team using Coulson wheels on their West Coast drive. Overall, West Coast Drive fits into games where Tank Drive does, but you might want to choose West Coast Drive over Tank Drive whenever you want to prioritize being able to turn and agility that comes with that over the simple brute force power and speed of Tank Drive.
So the last non-holonomic drive base we're going to cover today is Swerve Drive, which is a mix between an omnidirectional drive base and a non-holonomic drive base. And it consists of at least 3, but usually 4 of the modules shown left, with 1 at each corner. And each module has 1 motor that allows the whole module to swivel, and 1 motor that drives each wheel. And the benefit of this is that you get an omnidirectional drive base that has a lot of traction, and therefore it's a drive base that has good pushing power and is also maneuverable. The drawbacks of this are that it uses 2 motors per module, so at least 6, if not 8 motors just for the drive base. It's also very heavy because you have a lot of infrastructure for the modules, and it's also very, very complicated to design, implement, and program.
In that short clip, you could see a team implement Swerve Drive. It's a truly powerful drive base. Not one I'd recommend blindly, but if you want power, speed, and agility and have a competent set of people and the right machines to do it, it's certainly viable for almost every game. But even then, I wouldn't recommend it for all cases. Because the truth of the matter is, while Swerve Drive has a lot of moving parts and could very well be the most complex mechanism on your robot, this means that some of your team's precious time goes towards the drive base more so than any other drive base we're covering here. And by consequence of that, the other mechanisms are more neglected. It is harder to design, harder to build, harder to program, and harder to maintain or work on. As long as use as you see fit, but bear these warnings in mind whenever you're using it.
So the second group of drive bases we're going to cover are omnidirectional, and omnidirectional drive bases will always use holonomic wheels. But holonomic wheels will also see use in non-holonomic drive bases when you want to improve the ease of turning, like in West Coast or Tank Drive. There are 2 holonomic wheels that you'll see in use for FRC. The first is Mechanim Drive, which uses inclined rollers wrapped around the wheel, and there are left and right versions, and they're just mirrored versions of each other. The second type is Omni wheels, which have rollers that are perpendicular to the wheel, and this allows for very good strafing and lateral movement. So Mechanim will just allow you to move in any direction. Omni wheels are a little bit more for lateral movement.
Moving to the most common omnidirectional drive base you'll see in FRC, Mechanim Drive. You normally use 4 wheels for Mechanim Drive. 8-wheel Mechanim is possible, though there isn't much use for it. Mechanim Drive is almost as light as Tank Drive. It's almost equally easy to design and build, and although the code may not seem intuitive at first, you can more or less reuse it from year to year. Now, that being said, like a lot of drive bases you'll see in this section, it has the limitations of being slow, and you can see Mechanim drive bases being bullied by the other robots because they have so much less traction and are therefore much more easily moved. Micah?
So here's an example of a video that shows a Mechanim drive being used. So as you can see, Mechanim drive is very agile, but because it does use Mechanim wheels, Mechanim drive will sacrifice power at the benefit of mobility. The benefit of Mechanim drive is that it is one of the less complicated omnidirectional drive bases, so it's a good option for both rookie and veteran teams who want an omnidirectional drive base. It should be used in games where the robot does a lot of moving around or strafing, but the robot doesn't need much pushing power because Mechanim won't provide that.
Moving on to Kiwi Drive. Kiwi Drive is the widest drive base that we'll be covering, and it is still omnidirectional and quite fast. It is simple and minimalistic, and often doesn't require anything other than motors, brackets, channels, and some Omni wheels. It's not trivial to program, but it can be done, and it also can be assembled fairly quickly. A couple things to look out for is that you've more or less become the plaything of every other robot on the field, including some of the holonomic drive bases even. So if you consider this option, understand that you will both be moved around a lot, and also understand that the triangular shape means that your area to perimeter ratio will be different. So it'll be inconvenient, and it'll be inconvenient to implement mechanisms, and you'll have less space to do it.
So here's a video of a Kiwi drive in action. So as you can see, it is very light, it's very fast, and it's very mobile. And so therefore it should be used in situations where speed and agility are benefited in the competition, but you don't need pushing power at all. And one of the drive bases we're going to cover later is kind of an offshoot of Kiwi drive where it uses 4 wheels. So Kiwi drive should be used instead of this, it's called X drive, when you need a lighter robot.
X drive, or called in some groups slide drive, is a moderately common extension of tank drive, almost identical to tank drive, except for the replacement of traction wheels with holonomic wheels and a wheel running perpendicular. This wheel running perpendicular to the drive base allows for horizontal or lateral strafing, and this utility, because it's useful in so many games, makes this the second most common drive base that you'll find. However, note that, like all holonomic drive bases, it is slower, easily pushed, and normally you would have more motors devoted to the forward wheels than the lateral wheels, which makes it so that you're much better suited to travel like a tank than you are to move sideways.
So here's a video of H drive working. So as you can see, H drive does very well when it's strafing. And so H drive is a very lightweight and solid omnidirectional drive base to use. Because it can strafe, it is more forgiving for drivers. If you need to move the robot a little bit right, H drive can do that, whereas tank drive could not. And because it can strafe, it has overall increased agility. And another benefit of the H drive is that it's slightly faster than Mechanom, which is an advantage. The problem with the H drive and most other omnidirectional drive bases are that they're not very good at overcoming obstacles. Since they use holonomic wheels, they don't have very good traction, and so they'll struggle. For example, in First Stronghold, they will struggle with all of the terrain defenses. And also, I saw a couple questions in the chat. We'll go over questions at the end of the presentation.
X drive is more or less an extension of Kiwi drive to 4 wheels, with right angles to each other at 45-degree angles to wherever the robot is facing. Like Kiwi drive, it is light, can be achieved with direct drive, and since it has more motors than Kiwi drive, and because they're arranged in the way they are, it is faster than Kiwi. Although more powerful and has higher traction than Kiwi drive, it is still lacks pushing power, leaves something to be desired.
So here's an example of a Vex X Drive, which has all of the same concepts as an FRC Vex Drive. It's just made for Vex. So as you can see, X Drive is very fast and agile, which makes it a very competitive omnidirectional drive base. It works very well in applications where you need speed and an omnidirectional capability. X Drive also achieves very similar performance to H Drive. It just doesn't have the center motor and wheel. But the problem with that is that, one of the problems with the X Drive is that it doesn't have the same advantages as H Drive does because it doesn't have the tank setup. So it will have a little bit less traction going forward and backwards.
Moving on to some of the more complex drive bases, Butterfly Drive is certainly one in its own class, and although it's grouped with Octoconum, which is what we'll be doing next, it allows for a switch between traction and omni wheels, which makes it so that you have the advantage of traction when you need it and the lateral movement of H Drive when you want that agility. However, it is heavy, partially because you're including more wheels, partially because you're including more motors, partially because you're including pneumatics and the systems to support those pneumatics. It is more difficult to maintain than Swerve. It's easier to maintain than Swerve Drive, but harder to maintain than its two-component tank and H drive systems. And so designers who consider Butterfly as an option must really convince themselves that they wouldn't be performing equally well or almost as well with simply tank or Omni.
So here's an example. I think it's Team Spectrum's Butterfly Drive, and it shows the difference between the Omni setup and the traction setup. So since Butterfly Drive can switch between agility and traction, it is a very specific use case. So compared to other drive bases, its two components, H drive and tank drive, it is heavier than, because it's a combination of them. It uses more wheels and more infrastructure, but it is still lighter than Swerve, which is the heaviest drive base we're going to cover. It offers traction in one direction and agility in the direction perpendicular to it because it has the strafing wheel. Therefore, Butterfly Drive is best served in situations where strafing and traction are very crucial, but Swerve Drive would be outweighed by either its complexity or its weight increase.
Octocanum is a drive base that, for all intents and purposes, is fairly similar to Butterfly drive base. It includes 4 holonomic wheels, in this case mechanism wheels, and 4 traction wheels. It is similar to the Butterfly also in the sense that it's heavy, simpler to program than Swerve, but still fairly complex. But instead of leaving Omni wheels, the 4 Omni wheels unpowered and simply having 2 motors or 1 motor drive the center perpendicular Omni wheel, the Octocanum needs you to power both wheels for them to be of any use, because Mechanism isn't very useful unless it's powered. There are some teams get around this, some teams bite the bullet and don't. Either way, Octocanum has those drawbacks. More information about them will be in the next slide.
So here's an example of Octocanum drive. This is also by Team Spectrum. So like Butterfly Drive, it combines agility and traction very well, but also like Butterfly Drive, it is more complex, it's heavier, and unlike Butterfly Drive, this actually has less power. And this is because both Mechanism Drive and Tank Drive require power to all 4 wheels. So when you run an Octocanum drive, you're powering 8 wheels, but only using 4 at a time. This leaves you with 3 options. The first option is that you can change which axle your motor is powering. This is a good solution, but it's also very complex to implement. And the second option is that you have 2 switching mechanisms, one that switches which wheel is touching the ground, and another which switches which wheel is being powered. So you could have 2 clutches, one on each wheel, and then activate and deactivate whichever one you want. The third solution is just to have half the power. Like Marshall said, bite the bullet, and it's still a good drive base. Your drive base will still work, but you'll have half the power.
Track drive is special in the sense that it doesn't actually use wheels at all. It uses treads. So it takes the principles of tank drive and takes them to their logical extreme. And as a consequence of this, you are left with a drive base that is extremely powerful, moderately fast, and capable of traversing a wide variety of tough terrain. The fact that it has high friction from both of its treads means that you don't see it too often, as well as the fact that it is sometimes outperformed by Tank Drive and West Coast Drive, and in many applications it's outperformed by Tank Drive and West Coast Drive.
So here's an example of Tank Drive going over a pallet, which you'll see is actually about the size of the robot itself. So as you can see, track drive can be very useful where you need pushing power or you need to be able to go over obstacles or go up ramps or go over curbs. So a couple of sample use cases would be the 2016 game, First Stronghold, where there was a whole bunch of obstacles the robot had to go over. Track drive would have done really well there. Or the 2020 game, Infinite Recharge, where you needed to go over a 1-inch curb to get to the center of the field. Track drive would have also done really well there.
Okay, so if now is the time for questions. If we weren't clear on something or something we covered led to you having something you're curious about or some other question that you have, please ask them now. And also, Micah, please use this as an opportunity to tell me the questions that were asked beforehand. Micah, you are muted.
Thank you for that. Sorry. The first question is, what is the difference between having 6 and 8 wheels in tank and West Coast drives, but side number of wheels? Personally, I think that the biggest difference would be with more wheels, it's harder to turn unless you use Omni wheels, but it would give you slightly more traction because you have more ground contact. But I think the main difference would be that you have a harder time turning. What do you think, Marshall?
Yeah, increasing the amount of wheels or just increasing the traction on the wheels you have is a trade-off between your turn speed, how much power is required for you to actually turn in the first place, and the amount of traction and resistance you have to other robots.
So then second question is, what type of drive base have you found to be most accommodating to FOC robots? I would probably say that West Coast is the most common and most accommodating because it has good traction, but you can also turn really well.
I would say tank drive, but yes, you are accurate about that.
And then third question, what drive bases, what type of wheels are the most popular in FOC? And
that's a good question. I believe that in the examples that I've seen, a lot of them use Coulson wheels, partially because they're easier to maintain and also have a wide variety of different sizes. But the difference between the different types of wheels makes it so that, again, they have wide ranges of the amount of traction that they provide. So you might want to use a different wheel depending on the drive base. And again, I'd say the most popular one is the Coulson wheel.
I would agree with Marshall, but I also think that it really depends on what drive base you're using. So a lot of the drive bases in our presentation used Omni wheels, but there were some that could only use Mechanism wheels, so it kind of depends on what drive base you're running. And then the next question is, what drive bases are typically the hardest to design and install bumpers for? I would say Kiwi drive is probably relatively hard because it's triangular. Other than that,
hardest to design would likely be, well, Swerve Drive. The thing with Swerve Drive is there's a lot of examples out there, so you have a lot of examples that'll help you with that. But for some of the harder if you wanted to do it from scratch, Swerve Drive, and otherwise the hardest to design a bumper system for would probably be Kiwi Drive because it has a triangular shape, and the hardest to design in general with help would be Octocanum or Butterfly because there's less documentation on that, even if it in of itself is simpler than Swerve.
So our next question is, do you think teams should utilize different drive mechanisms for offensive versus defensive bots? And if so, which do you think would work best for either playstyle? I think that's a really good question.
Sorry, go ahead.
Go ahead. No, go ahead.
Defensive bots and offensive bots both are benefited in. So in the game Recycle Rush, my understanding is correct. Both teams usually stay stuck to their sides of the field. And in those examples, there really were no offensive or defensive bots. Bots would do their job on their side of the field. And so for offensive and defensive bots in games that are more competitive and have a more mingled field, such as, Deep Space, you would want to incorporate the most traction you could possibly get away with because the other teams will be interfering with you and trying to move you around, and choosing a holonomic wheel may lead to issues later down the road.
So I'd agree with Marshall. I think you can use both, but you need to keep in mind that holonomic drive bases will get pushed around more. So on a defensive bot, you might want to use non-holonomic so that you don't get pushed around much.
And that's true. Like with a defensive bot isn't much use if it can't actually interact and interfere with the other robots.
Yeah. So then next question is, what considerations were taken for chassis type design for the 2020-2021 season? So like we mentioned a little bit in our presentation, I think the biggest consideration was the curb on the field. Not the curb, but I think you guys know what I'm talking about. So West Coast and Tank and Track would have done better at going over that than some of the omnidirectional drive bases.
With that being said, for the skills challenges, there were 3 different challenges that were devoted to agility and speed. There was the Galactic Search, Hyperdrive, and I forget the third one. There were, either way, you could get, and since you were allowed to do 3 or more of the 5, you could get by with just a drive base and an intake mechanism. And so for the 2020 to 2021 skills challenges, you might want to invest in a holonomic drive base or a drive base where you don't need to consider other robots at all because they're not going to be a concern to you. So during that season, I think it would have been a great idea to incorporate either a Kiwi drive, an X drive, or in general, a holonomic drive base, which you would normally discount because of its capacity to be pushed and bullied around a lot.
Yeah, that's a really good point, Marshall, for the skills challenges. An omnidirectional drive base probably would have done better because you don't have to worry about any being pushed around or anything. You can just worry about agility. And then next question is, does bumper attachment change from drive base to drive base, or do you use the same process each season? Personally, I think although you could change it, there's no point. As long as you use the same frame pieces each season, you can just reuse your same attachment mechanism for every drive base.
Yes, if you have the same. I'm sorry.
Except for Swerve, you might need something different because Swivel Drive the Swerve modules are relatively tall, so your frame will be a little bit higher than the wheel. So you might need to design something else for that.
Yes, if your drive base is the same size and shape as it is from year to year, which you realistically can have it be that, assuming that the rules remain relatively same for size limitations, unless you wanted to do a drastic switch over to Kiwi or something.
And so next question is, what shop equipment and processes do you use to manufacture your drive bases? So for us, I think that a bandsaw is really important for cutting all of the frame pieces to length, as well as we use a mill, but you could probably also use a drill press to drill all of the holes for the bearings for the axle shafts.
And something to note is for some of the drive bases that their main advantage is the fact that you can get them with commercial off-the-shelf parts and running very quickly. So for Kiwi Drive and for X Drive, you may not need to manufacture custom rails or custom brackets and just purchase those off of West Coast products or Vex Pro.
Yeah, and then so next question is, would you recommend picking 1 or 2 drive bases and perfecting them and using them from year to year, or using a wide variety depending on the year? And I think that's really up to the team. Some drive bases will do better in competitions than others, but it's also good to have a drive base that you know will do really well and you know how to work on, and it won't break all the time.
Right. So I believe that there's a trade-off between finding the optimal drive base for every year, and it varies for every year, and using a drive base that you know how to do well and your team knows how to do well. That being said, it is also incredibly a good learning experience for trying to learn and construct and program a new drive base.
Yeah, so the next question is, what are the ultimate wheels to use? I'm not sure that I really have a great answer to that question because it really depends on the drive base you're going to use. For a non-holonomic drive base, like we said earlier, I think it's probably Coulson wheels. For holonomic drive bases, both Mechanim and Omni have their place, and they're definitive. You can't swap them out for each other. What do you think, Marshall?
I personally have a soft spot for Coulson wheels because they are widely applicable and widely customizable for the application. So you see them in use in many mechanisms, such as flywheels of shooters, components of the intake and indexing systems, and usually you don't use them for the color wheel of last game, but you could theoretically. So coast and wheels are used everywhere. They can be used in most applications, and they also require little maintenance, and that's why I prefer them to the other types of wheels.
Yeah, I agree. So then our next question is, does a Swerve drive base have more or less traction than a West Coast drive base? And my answer to that would be, it might have slightly less because it only uses 4 wheels as opposed to 6 or 8. But overall, it uses the same, they both use non-holonomic wheels. They both have very high traction.
I'm going to have to disagree with that because for Swerve drive bases, you can use more or less the highest traction wheels that you can find, because you don't need to worry about turning your drive base itself as much as you would turning the wheels individually and moving independent of the orientation of your drive base. And so for that reason alone, you see Swerve modules incorporating things like Versa wheels, things like treaded traction wheels, because they can get away with it and not have to deal with the issue of turning.
Yeah, I actually hadn't thought about that. That's a really good point, Marshall. On a West Coast drive, you don't want to use the highest traction because you won't be able to turn very well. So
this is an example of Swerve module. I believe it's using a Versa wheel.
Yeah. So then our next question is, for younger teams, do you have any recommendations to the Andy Mark Kitbot chassis to make it more competitive?
I'm not familiar with the Andy Mark Kitbot package contains, frankly. So unless Micah knows, I don't know if I'll be able to answer that question very well.
I'll do some research and then we can come back to that one. That's a good question. What are some of the weirdest drive bases you've seen?
Okay, so sorry, go ahead.
No, go ahead. I'll do some research on.
There was one team that had different track modules and incorporated them into a Swerve drive base. So you could pivot 4 different treaded traction. You could pivot 4 different treads and maneuver from those. I think it was for Stronghold.
Yeah, I mean, this is my first year of robotics was 2021, so I really haven't seen too many. But yeah.
Out of the selection here, the ones that you'd see the least often would be Butterfly, Octocanum, and after that, Kiwi.
So then our next question is, which motors would you recommend for the different drive base types? Is there clear standout use in most situations?
Sorry.
Go ahead.
It depends on your team, what your team is familiar with, and what your team's budget is. Because the Falcon 500 motors offer the highest motor efficiency out of any motor, I believe. And so you might want to use those where efficiency is crucial, your team has a big budget, and your programming and electrical teams are familiar with them. But that being said, a lot of the motors offer similar performance, and you really should go with what your other sub-teams think you should use.
So then I'm going to go back to a previous question about the Animal Kitbot. And from my research, I found it looks like a West Coast drive. So I think that the biggest thing that you could use is to swap out the wheels. See if you can find wheels that either, if it's not turning very well, allow it to turn better, or see if you can find high traction wheels that don't affect the turning very much. So then our next question is, are there any holonomic wheels that have good traction? And I don't know if we made it like, go ahead.
So the way holonomic wheels work is they require to have little traction so that they can move and be manipulated and pushed in any direction. That being said, I believe out of Mechanim and out of Omni, Mechanim offers higher traction than Omni.
Yeah, I think that Machina might have slightly more ground contact than Omni, and that would give it a little bit more traction. But as Marshall said, both of them are intended to have as little friction and ground contact as possible to suit their purpose. And another question, do any of these wheels have a problem with weight distribution? And for that,
They're designed to be uniform, as they have to be circular in nature for them to even work. So I don't think I think that unless you modified a wheel deliberately to have off balance, to make it so it was off balance, you wouldn't encounter that issue.
yeah, the only thing I'll say is it's not really a problem with weight distribution, but mechanism wheels do have the opposite sides. So if you used all of one side, it wouldn't work too well. Next question, would you recommend to always have a full rectangular box for the drive base unless using a Kiwi, or all you really need is a U? I think that you can totally get away with the U. In fact, it's hard to not get away with the U if you have an intake system. What were you going to say, Marshall?
There are some over-the-bumper systems that make it so you have a closed box intake, but you don't necessarily need the front rail or the back rail, depending on the orientation of your robot. It's mainly a issue of whether or not you have the intake system that can get away without it, in which case you'll definitely include it because it gives you more structural stability.
Yeah, I agree with Marshall. As long as your intake system can give you the stability, then you could not even have an end piece on either side, as long as you can connect your robot together well enough that it won't fall apart. So as long as you have a good intake system, I would recommend a U. And that's all of our questions for now.
Perfect. Do you two presenters have any last advice for any of our viewers today before we go to the break?
No, that's about it. Thank you for watching.
I can't think of anything.
Okay, perfect. Then we'll call it here. So as a reminder, we'll be back at 5:50 with our training CAD team panel with representatives from Team Spyder, Robot Dolphins from Outer Space, Code Orange, and the Super Nerds. So we'll see you then. Thank you all for watching and see you soon. Okay, welcome back everyone to our second workshop today. We'll be starting the Training a CAD Team panel right now. And first of all, I'm going to have our presenters introduce ourselves, starting with me. I'll be a moderator and also a panelist for this evening. And I'm Kyle from Team 5199. I've been in FIRST for 5 years, or in FRC for 5 years. And I just graduated. So this is my 3rd year as design lead. I have spent the past 3 years as design lead designing a training curriculum for my team that's 30 pages. So I'd like to say I'm pretty experienced in the realm of CAD training. And off to Eli.
Hi, I'm Eli Uva. I'm a mechanical mentor for Team 3055. I'm a sophomore at San Diego State University studying mechanical engineering, and I was an alumni of Team 3055 from 2016, and I graduated in 2020. And yeah, I'll hand it off to, is it Alan or Marshall?
Alan?
Hi, I'm Alan. I am the mechanical design lead of Team 3476. I've been design lead for the past, I think, 2 years. And yeah, I just have fun designing robots, and I just really enjoy doing CAD and doing mechanical design.
My name is Marshall Hammond. I like to use SolidWorks. I am the systems engineer for Team Spyder.
Great. And just so everybody knows, while most of our panelists use SolidWorks as their primary tool, this panel is not restricted to just teaching SolidWorks. We're going to be focusing on the principles behind and the workflow behind CAD training. So this can be applicable to any program that you're using, whether it's Onshape, Fusion 360, Inventor, all those will still apply because we're really looking at the principles behind it rather than, oh, I'm teaching construction lines in SolidWorks this way. So we hope that it's open to all programs. We're going to start with a really basic question so we get to start kind of peeking behind the window into our different teams' philosophies behind CAD training. And so we're going to start with more of a general training philosophy before we get into the nitty-gritty on CAD stuff. And our first question is going to be, what is the learning process your students go through with CAD training? So do you focus on independent work using written or video tutorials, live instruction, a combo of the two, or professionally produced tutorials? And I'll start. So on Team 5199, we try to appeal to a wealth of different learning strategies. And so we have a huge emphasis on documentation for our curriculum that we are continuing to document, so make sure we can pass it down and then keep improving on it so that we have a record of what's been done in the past and what can be done in the future. And so in that realm, we have, as I mentioned, our 30-page CAD packet that just keeps growing. And so that's our written documentation that both students and instructors can use to teach or learn. And our chat moderator will put a link to that curriculum in the chat if you're interested in checking it out. It's still being further developed, but yeah. But we also find a lot of our students prefer live instruction for CAD and to an extent programming as well. And so we offer the same lessons we do for CAD in our packet. We teach them live as well. And so that allows them to, one, have the packet as a reference tool so they can go back and check the steps that have been done if they miss something, but they can also come live and get their questions answered if they're stuck, for instance. And so that's our process there. So we try to attract multiple things. Though for us, we found that we prefer using our kind of in-house curriculum opposed to like a professional one, like Solid Professor or the integrated SolidWorks tutorials. So we can make sure to focus on really everything that we want to make sure we teach, because sometimes there are things that we don't use or don't need to teach, or some things that we want to emphasize more. Okay, so off to Eli.
Yeah, so on Team 3255, we do pretty much all in person or, online, but it's normally an instructor, whether that's a mentor or a veteran student, is teaching the CAD. And the way we kind of like to do it is we'll start off with really basic things, teaching, camera controls, basic sketches, stuff like that. And then we'll slowly build onto there. And then as soon as we're done with that, we'll always do a project. So we like to focus on project-based learning, just because that gives the students a really good emphasis for what they'll be doing during build season, which is not very far away if we're teaching an off season. So we really like to make something like a drivetrain or maybe a mechanism we've never made before, like a style of shooter or something like that. So that's kind of the process we go with.
So on 3476, we like to focus mainly on live instruction, kind of like how Eli runs his trainings. And it usually involves like a presentation that goes over some of like the basic concepts of SolidWorks, and then maybe like a demo that goes over that kind of just shows these features or whatever I'm teaching in action, and then an activity as well. So I find that like activities really keep any like new students engaged in learning CAD.
On 6022, students work on our FTC team first, usually during their rookie year, to get the principles of mechanical engineering down. After that, they advance to do some supporting roles on our FRC team, and after that, they will either head a mechanism or the project itself. Other than that progression, aside from that, we also have a folder that gives tutorials made by students and mentors. So if someone has a question or wants to build something, and if someone wants to have a question or build something that's outside of that, they can consult either a tutorial on YouTube or ask an alum, mentor, or other student on the team.
Okay, great. And I think Eli's statement about project-based learning is also great. I definitely forgot to mention it, but yeah, we do use that as well in our later CAD stuff that we'll talk about a little later as well. I think personally, every team should really have project-based learning, especially for CAD, but the hands-on experience is what makes them ready to go into a season to be able to apply hands-on again with a whole new challenge. That's a huge thing. And I also just would like to emphasize that the importance, at least I hold with documentation and our team has, and ensuring that you have something to pass down, because we've been in the situation so many times where we can't reach alumni and don't know what they did. And I think a lot of teams have been in that situation before. So even if you aren't doing it like the full documentation thing where you're going step by step into every single little nitty gritty thing that you've emphasized or mentioned to make a guide for students and instructors, as long as you're documenting at least some of the stuff that you're teaching, it's really helpful for future years. So that's a good guiding principle for really all things in FIRST, not just training and not just CAD training specifically. Okay, so our next question is going to focus on teaching the basics in CAD. So our next question, as appropriate, is what is your workflow for teaching basic CAD? For us on Team 5199, we go through basically 5 lessons, and because we're part of kind of a class, we also have a club component. We try to get everybody, at least in the class, to go through all 5 of these basic CAD lessons to see if it's something they're interested in, but also to make sure that they have the general skills in case we need something like last minute or need them to go look at a part that we already have CAD'd but not a drawing for already, and especially for just looking around assembly, seeing how they get assembled, because we don't always have time to make assembly drawings or have someone guide someone through the assembly. And so our first lesson is really the simplest of things, because sometimes I'm honestly incredulous at how much prodding people need just to get into the basic groove of SolidWorks and CAD in general. And so we go from everything, because some of our people are using like Windows for the first time with SolidWorks. And so we go from extracting zip files and downloading files and finding where they are in the file explorer, both inside and outside of SolidWorks. And then we start to teach them basically view orientation, rotating, zooming, because it does take a while to get adjusted to if you haven't used these programs before. And so that's our first day. And then also on that first day, we do something with the evaluate tab in SolidWorks, and another software would be pretty much anything you want to do with measuring and evaluation of different lengths and areas and measurements. So we think that's the best way to get them started with the program. And so we do it that way. Then we go into continuing to get them exposed to SolidWorks, because I know some teams like to teach every little thing at once. Like they go into, here's everything we're going to use on the first day, just to show where everything is. But on our team, we take a more staged approach. So lesson by lesson, we go into more detail on things that we haven't touched yet. So lesson 2 is continuing to get them exposed to SolidWorks, specifically the dimension tool as a kind of a preview. And to do that, we teach drawings. And so we give them a pre-made part. In lesson 1, we give them a pre-made assembly, and we give them a part in lesson 2 to make a drawing from. And we go through both our personal standards of drawing, but also it really helps them get used to, like, at least in SolidWorks is the example I'll use, the left flyout popping up when you use something new in a tool, because people really don't know where to go sometimes, at least in SolidWorks, and probably also other programs as well. And so that we just start to ease them in, even if it's a little boring at the beginning because they're not getting to make their own stuff. We think it's important to ease them in. And then I'll quickly go through lesson 3, 4, and 5, but lesson 3 is getting exposed to everything sketches. So we kind of just use everything that you'd normally use in FRC for sketching. So we skip splines and stuff like that for that basic training, but we do everything that you would normally have with geometry. Lesson 4 is when they start their personal project, because it's when we go over making things 3D. So extrusions, obviously, but also other features that you use in 3D. So cuts, holes, fillets, chamfers, etc. And then they start making their own stuff because they're finally at that area where they can make their own things with the skills they've learned. And then lastly, we do assemblies with a guided part they make, or one guided part they make in lesson 4, which we do a gusset. And then we also make them make a part from a drawing in lesson 4 with the tools they've already learned. So we make them do a box tubing and a gusset that way. Okay, on to Eli.
Yeah, so on the Super Nerds, it's very similar to how the Dolphins do it, but we don't necessarily do lessons, but we do kind of stages of learning. We don't split it up as neatly, but basically when we first start, we always show off the previous robot. So we'll show the CAD file from there, give a quick overview of what it is and, you know, the different things, because people don't know what like parts are or anything like that. And we just kind of go in very high level describing the little bits and things about it. So from there, we will do instruction where everyone will watch a presenter sort of design a very simple part in SolidWorks just to showcase, you know, where you start and how eventually that can turn into something like the robot. So we'll do a little tutorial and then we'll have all the students follow through and make the same part the first person made or a part that is similar to it. And then from there, the second stage is when we start teaching all of the different tools, whether that's extrusions, you know, more complex 2D things. But really that's when we get into making stuff 3D, and that's where it gets a little more complicated. So always make sure to move quite slowly through that stage and answer everyone's questions, because that can be a little bit overwhelming, especially with all the hidden errors and stuff popping up. Then for the third stage, and again, all these stages are before we start jumping into project-based stuff. For the third stage, we'll get into assemblies, you know, how things will interact with each other and mating them together. So I don't know if that term is used in all 3D modeling softwares, but it's basically when the little pieces, you know, combine with all of the other ones to make something bigger. So on that stage, we also teach about CAD sharing and conventions, and that's when we touch on GrabCAD, which a lot of teams use. And that's also when we teach how to use our common parts library, which basically has all of our bearings, bolts, everything saved. So then you don't have to re-download it every time. So yeah, and then from there, we jump into, I guess you could call it the fourth stage, which is when every student will make their own drivetrain or shooter or whatever mechanism we choose for that year. Typically it is a drivetrain though, because it's a simpler mechanism. But yeah, and then from there, the students have a pretty good basis of SolidWorks, and then that's kind of about when build season rolls around. So yeah.
So on 3476, we kind of start off by teaching the basics, kind of like how Kyle and Eli mentioned. So we just start off with like basic mouse controls and like basic keyboard controls and like how to control the camera. But then as we go kind of through, this process takes a couple weeks. As we go through, we also teach like sketches, like relations within sketches, and like the features for 3D to make on 3D objects. And usually at the end of this kind of basic stage of the CAD curriculum, it ends with a creation where all the students make their own gearbox. So this is kind of like a culmination of all the skills that they pick up through the weeks, where they create a fully working, like maybe like a one-stage gearbox. And then on top of that, I also like to teach pocketing at the end of that kind of gearbox stage. So that kind of, in my opinion at least, I think pocketing is like a, it's kind of like a symbol of like everyone's capability, because pocketing involves a ton of different, a lot of sketch knowledge, a very complex knowledge in how to use sketches in relations. So I like to use that as kind of like a, as kind of like an indication that, oh, everyone knows that, oh, I'm capable at CAD, I got this. So yeah, that's kind of how we teach the basics.
The development of someone going on a CAD team usually goes along the progression of first, they understand how to work with SolidWorks or whatever CAD program they're using. A lot of our team uses Inventor, which includes camera control, where to find certain tools, opening parts, creating parts. After that, we teach them how to import parts from third-party suppliers such as Vex Pro, AndyMark, or West Coast Products. Then they learn how to use those parts in assembly, which includes inserting the parts and mating them together. After that, they get to make their own parts, but they're simple, which are either sketches or more or less sketches with depth. And after that, we can get into some of the more complex parts and assembling those. This is where we teach most of the features of extrude cuts, boss bases, revolved boss bases, cuts, fillets, so on and so forth.
Okay, it's great to hear a bunch of different approaches, and that just demonstrates that, you know, no matter what your structure is, as long as you have a structure and you are making sure that students are working through it, you are able to have a successful CAD team. There's no one way to train a CAD team, and that's what we want to definitely demonstrate with this panel. Some ways might be better than others for your team based on what its needs are and how it progresses. You know, a class-based approach is probably going to be different than a club-based approach, but it doesn't have to be. It just depends on the commitment and availability of your members. So making sure to try a couple different approaches if you're looking to change your CAD workflow. That's always an option if you want to look for a more effective training method. Our next question is going to move into a little bit more of overall CAD. We kind of focused on basic there. Some teams did talk a little bit more about more of their advanced process as well. But this next question is specifically, how do you structure your CAD training process? So this is basic, intermediate, advanced projects. Kind of what do you do in that realm after you're done with basic CAD? And so I'll start again. For our team, we kind of have 3 phases of CAD. We have our basic CAD phase that I described already. Then we have our intermediate CAD phase and then our advanced CAD phase. And you kind of have to get through all 3 of those phases until you're ready to be on the design team. And sometimes that takes more than 1 year. But our intermediate stage starts with what Eli was mentioning at the end of their basic stage. And that's once you know that you want to go and pursue CAD, we start to teach you GrabCAD, which is what we use for file sharing. And I think most teams are in that boat unless you're using Onshape, which has its own. But we do that, and we also do our common parts library. And I cannot underscore the importance of having a common parts library so that you don't have to download thousands of files every year for all the fasteners and bearings and whatnot. So I know Team Spectrum has a really great one. I think Code Orange also has one as well that they have released to the public. So those are both great resources, at least for SolidWorks-based ones. And then so for intermediate CAD, we also do a drive base, specifically a West Coast drive, because one is pretty much the most common drive base, at least that our team uses, but it also has enough complexity that it's ready for students to start showing their skills and using our different parts libraries and templates and whatnot. But at the same time, it's enough that they can be guided through the process, and there's a lot of resources out there. And so typically we'll have one of our leads, and in the past years, it's been me, teach a guided drive base through the West Coast lens. Though we do have, towards the end of that project, students vary their specs. So it's not everyone's doing the same drive base. They have their own creative freedom and can do a bunch of different types. So we'll have some people do 4-wheel, some people do 3-wheel. Some people do drop center, some people do chain, some people do belt. So we try to vary that up a little bit so it's not, you know, just droning on and monotonous. Everyone gets the same one. It's not like a 1984 type deal. And then for our advanced CAD project, sometimes advanced and intermediate kind of mix in terms of the phases based on the availability of our leads. But our advanced CAD stage is essentially reverse engineering a mechanism and making your own. But we pair or group students up to make sure that they're also working together on a systems integration project. So for instance, this year, which is kind of the first year we're doing like a big summer project like this, we are assigning each group of students, and we have 3 groups of 2 this year, and they each have like a pathway. So for one, we have a climber and a buddy climber. And so for one group, they're each designing different climbers based on different game specs, and then they swap it to build a buddy climber for each other, so they have to work around each other's build specs. Another group is doing a shooter turret transport deal, and then the last group is doing an arm elevator intake deal. So we're trying to get experience by doing varied projects, but also work together, because that's something that you don't really get a lot of practice in basic training. So yeah, that's our CAD workflow. So it's a pretty big balance of guided practice, but also independent working. Off to you, Eli.
Yeah, so basically, from our, the stage that we were just talking about, where I ended the drivetrain or whatever project it is, on our team, we also like to modify the previous year's robot, add another mechanism to that. So that's another potential project for new people or veteran students to sort of jump aboard and get some more CAD skills that are more related to actual engineering rather than just learning the program. So we really like to build a new robot, especially because the kids will get to drive it at an off-season event. And I bet it feels really good seeing your first mechanism on the field actually driving. And I remember when I was a student, that always was nice to see. So we always really like to, edit our robots and do stuff like that. Another thing too that we will do is sometimes we will start from scratch and build a new robot. We can't do it every year based on the time, but we will always, make small modifications to our previous year's robot. And yeah.
So our CAD training is kind of split up into two major parts, which is the basic stage that I mentioned before, as well as the kind of more advanced stage. So when newer students complete the basic stage, they move straight to the advanced stage. And then when like veteran students who have already CADed build seasons for the CAD, they just go straight to the advanced. And pretty much what the advanced stage is it just involves a lot of off-season projects. I feel like doing off-season projects is really fun for everyone, and also both helps improve like our shop or our CAD room. So it's kind of a kill two birds with one stone situation. So like these off-season projects could be like, oh, if we need like a new shelf in the shop or something like that. It's really great to have CAD students. They can choose if they want to design an off-season project, or it could be something like a subsystem on the robot that. But usually we try to have students who choose to do an off-season project go and design something like a shelf in the shop that can be really built, because I think it's really encouraging to see that, oh, my design is being built and that's my design. But it's really just up to, when we get to this stage, it's really just up to the students to choose if they want to do an off-season project. We don't really try and push them too hard because CAD can sometimes be tiring and it's right before season, so we don't want them to burn out.
All right, for our team, you usually have completed the equivalent of the basic CAD phase by the end of the first year for your FTC team or before build season for your second year. And at that point, they're prepared to make parts for the FRC team. And I've already mentioned this, but after that, they're usually in a position to orchestrate one of the major components of the robot and work together with the people they've spent 2 to 3 years with to integrate that work with someone else who's at a similar progression, a similar point in that progression.
Okay, great. So we've heard a lot about different approaches to off-season projects, from Code Orange's approach with, doing stuff around the shop, but also doing whatever interests their students. And then also, I guess, our other teams on either working on a FTC team and for super nerds and robot dolphins, making mechanisms, whether it's for a brand new off-season robot for the current season or for older seasons based on past specs, and reverse engineering that workflow there. Okay, so our next question is going to cover a little bit of a question that we have in the chat, in addition to, I guess, a little more of an extension of that. So our question is going to be, when does your team start training students, and about how much experience do students accumulate before the season starts? This is also kind of asking, how long does it usually take for the average person to fully learn CAD? That's one of our chat questions. Okay, so I'll start here again. So our team is recently started doing a more intensive summer off-season training, especially as we're coming out of the pandemic, and we started to have more of a need for that as a lot of our veterans graduated last year, including myself. So we have a whole intensive summer training session, and for CAD at least, what that looks like for us is we kind of lead basic CAD training 3 times a year. So one of them is the summer, which we're doing right now. And we have some great people working through that. And then we lead it with a bunch more people during the school year around September, October, sometimes reaching into November. But we try to get that done relatively fast so that we can do some more intermediate and advanced CAD as it gets closer to season. But we do a second round for our class students and any club students that want to kind of audit it. And then after like the real CAD part of season's been finished and starting to move into competition season, but we kind of lead a third round of CAD for any new students that might have popped up during the season and just got interested and started joining, or any people that didn't learn it beforehand or wanted to further refine their skills. So we kind of lead it 3 times a year. And then intermediate CAD and advanced CAD, we try to do an advanced CAD project in the fall semester as well, so November, December-ish. And then intermediate CAD availability varies. That's our guided drive base, because we want everyone to be able to do that, but it's not necessarily a requirement, because sometimes we have students with a huge aptitude already for CAD who already have experience and don't necessarily need to go through the drive base project right away. They're ready to go straight into working with a alumni mentor or an experienced CAD team member and do an advanced project early. So intermediate CAD, we try to also do in that first semester, that fall semester. So sometimes we do in November and December. Other times we just do an advanced project and kind of pull people up by their bootstraps there. For us, CAD training is kind of a 1.5 year long process for if you're looking to be on the design team. Sometimes students are really voracious readers and would go look up things on their own time or go straight to the packet on their own time and are ready to jump in kind of right away. So it varies. But I guess for our team, for really getting all the fundamentals down and being ready to fully CAD for FRC, I'd say it takes about 1.5 years, a year if you're lucky, or I guess a season if you're lucky, you know, an off-season season process. So yeah.
Yeah, so on the Super Nerds, it's normally a full season to season and a half, maybe 2. And again, it really varies for how much time each student's putting into CAD. Science will have freshmen who just joined with mechanism on the robot. Sometimes it'll take 2 years, 3 years. But really the way we structure it is we will sometimes do some introductory stuff over summer, but normally that's just to train veterans to get them ready to teach rookies the following year. And our school year starts in August, so that's when we start doing meetings. And then the first 2-3 weeks, that's getting the younger students up to speed with CAD, so they'll be ready to work on our revamped robot from the year. So what we really like about that, you know, second version of the robot is the veteran students will always have really hard things to do on the robot, and then the rookie students will find little ways and to help the veterans, or, you know, head up their own subsystem or something. So typically a student, after doing 1 full season, including off season, they'll be ready to have a mechanism. And most of our CAD team, although it's normally around 4 to 5 people, sometimes it's a little bigger than that. All those students will have, you know, 1 year, 2 years of experience, and then from there they'll start teaching the next generation. So that's kind of how it works.
So for Code Orange, our CAD training kind of starts in the fall, so maybe September, October, and goes pretty much all the way until winter break. So that's like December 15th or something. And then when season starts, then the new CADers just jump right into CADing. But I would say new students, they will be fully kind of knowledgeable about SolidWorks and CAD probably by the end of their first season, because a lot of CAD is like figuring it out on their own and just doing a lot of practice. So when they get thrown into their first season, their first build season, and when they start designing the robot, they usually design something small and they just learn how to do it well. It's like a hands-on approach to learning CAD. So yeah, so like kind of funny story, what I did my first year in 2018 was I spent 3 weeks designing an often smaller subsystem. So I spent 3 weeks designing a carabiner hook. So I spent 3 weeks essentially designing 2 plates and like 5 standoffs to grasp onto a bar. So yeah, new students usually design a smaller subsystem and just dig their hands in and start just learning CAD while they're designing.
So FTC, if you don't know, starts in the fall. So that's when new students start to pick up their CAD skills. After a year of FTC and after the FTC season ends, the FRC season is still continuing. There's some minor participation in FRC. In the off season following that, and after that, they're ready to build parts for the FRC team, as I've mentioned in some of the previous questions. And after they've done either some of the either a minor mechanism, such as the color wheel for last year, or supporting parts for the main mechanisms, they're able to, as I said, work on some of the main mechanisms.
Yeah, great to hear. And I think, like what Alan and Marshall were saying, the sooner you can get people involved in real FRC CAD, not consigned to off-season projects, I think that's the better. That's the way I learned personally. I did like a passive intake my first year, which was Teamworks, and then graduated into like more stuff. I then did a full intake and a drive base. At least that was my personal experience there. But yeah, and for our team, sometimes it does take longer. But we are hoping, at least for this year, to have people start jumping in for the season. But in past years, it's taken us a little longer to teach. But if your team has the teaching power and you're able to get them ready for that first season, if you can do, an off-season long training set or training regimen and get them ready to start contributing their first year, that's great. But some teams where you have smaller CAD teams and they're more tight-knit and not everyone is able to teach or mentor students because of the heat of season. Like our team was kind of in that boat this year and last year. Well, I guess last year, because this year we didn't really have new students ready for CAD because of the pandemic. But yeah, I'd say that definitely try to get people involved as soon as possible. But if it doesn't happen, it doesn't happen. And I think there's, they can still get experience by watching and also just practicing on their own time, like Alan was saying as well. Okay, our next question is kind of in that vein. How do you encourage students to improve their skills on their own time? So this is kind of going to be just a quick question for our team. Part of our basic CAD curriculum, they can kind of earn extra credit points by doing whatever model they want. And we try to encourage at the beginning phase, you don't have to do anything for FIRST. We want you to get experience with SolidWorks by building stuff that you're excited about. So whether it is, a gusset that they're building for a project if they want to, or whether it's a really cool sword or a frying pan they want to like 3D print. And those are both projects that we've had in the past. We just encourage them to get crazy with it. And we really do encourage them to explore things that might not often be used in FRC, but they could be. So we like giving them just extra credit projects pretty much for that section, and they can make whatever model they want. Okay, off to Eli.
Yeah, so basically we have we have students sort of I guess research videos, but what we'll a lot of the time say is to look up different robots, and from there look at how they work, stuff like that. Now from there, sometimes students will maybe make a replica of that in CAD. Sometimes we'll have students look at tutorials, but it's really up to what the students want to do. But we will always tell them, like, it would definitely help you get a little bit ahead. But again, we're just a club. We don't have like a class on campus for SolidWorks or anything. So really it's just up to how much a student wants to do. But we do provide them with a laptop out of the 5 that we have on our team. So they will be able to do stuff at home if they do not have one. So yeah.
So I think I mentioned this in one of the earlier questions, but yeah, so our team likes to place a big emphasis on off-season projects. So yeah, so it's kind of both the way for students to improve their own CADing by designing something that whatever they want, or like a shelf or something in the shop. And it also gives us the opportunity to build whatever they're designing. So if we need the shelf, then we can build the shelf and then we can put stuff on it. So it's kind of, we really like doing off-season projects.
Yeah, our team incentivizes students to pick up some projects on their own, either if it's something completely separate from the team or some off-season project that are doing with some of the other students. And they can either consult mentors or some other students to help them with that. And that's assuming it hasn't been documented or something similar has been documented by a previous student in the overall folder for off-season and other projects.
Okay, great. As we start approaching the end of the panel, we'll probably go a little long. We're going to kind of go into a rapid fire round of questions. So we're going to just do kind of shorter responses and a little bit less intense questions, but that are still valuable, I think, to share our opinions on. So, okay, this is kind of from the chat, but also from one that we have ready. Teddy asks, what is the most complex function you teach? And as a joke, do you only do extrusions? And so this kind of also could be, what is the most underrated CAD school or skills, tools, or principles that you think more teams should teach as well? So both of those angles are fine. For us, I guess this is our approach to it on Team 5199 is we try to make our CAD or our CAD team have a low barrier to entry because we don't like teaching all these complex stuff like weldments and whatnot, because it makes it very hard for students to get into it without knowing everything. So as much as we try to make sure students are ready, sometimes we do need to throw them into the thick of it during season with only the basic skills. So we try to make sure that we really only CAD using those basic skills. So we do extrusions, we do fillets, and we do that, but we also promote a lot of problem solving with how you can use those basic skills to approach a part and make it that way rather than, you know, a shortcutty way that you might learn in a more advanced CAD class at the university and whatnot. So for us, I'd say almost keep it simple, but also, I guess, fun CAD skills to teach. I'd say are really just, you know, problem solving. It's not part of your program, but it's something that is an emergent property of all of the things that you learn about your program. So like we have a formative CAD final of some experience. It's, you know, you get 100% if you keep retaking it till you get all the questions right, and it promotes application. You know, they've learned all the skills, they just need to apply it now. And so we try to promote that skill through a little application test that way. Okay, next one. Eli?
Okay. Yeah. So one thing we spend a very long time on in CAD training is basically sketching, which is as funny as that sounds. We really draw every part to be as adjustable as possible. So every time you design something, you think, oh, I'm not going to change this until we have to change it. So we're always changing our parts, changing dimensions, adding stuff on. So we always try to make our sketches as simple, easy to read, and adjustable as possible. So I got to say this year, although we were designing a 3D model of our field for our game instead of a robot, we still did the same thing, and we always ask the students, okay, this is great and it'll work, but how can you make it more adjustable? And then from there, they will modify their sketches and use a lot of construction lines and stuff like that.
So I'll start with the most complex thing that we teach, and I would say, I mentioned this earlier as well, I would say it's pocketing. Pocketing is kind of like what Eli mentioned, it's a lot of sketches. So just like the combination of a ton of sketches and like knowledge and relations and like the trim entities feature, that's kind of the most complex. But the most like kind of underrated, kind of interesting skill that I like to teach is what I love to teach is mouse gestures. So in SolidWorks, at least, if you hold your right click, a wheel can show up and you can quickly select tools very quick, like without having to go up to the menus. And I just love teaching that because it just speeds up the CAD workflow like 3 times.
I think this is a good question because our team doesn't usually teach some of the more advanced tools, especially when they're doable and achievable with a system of simpler tools. Maybe swept boss bases are the most complex things that we see each other doing, especially with 3D sketches. Speaking of which, my favorite CAD tool is probably the 3D sketch. I don't see it put into use too often, primarily because it's often slow when it could be achieved with a set of simpler tasks, but it can do certain things better than anything else. And similar to Eli's point, you try to disincentivize people from using 12 or so dimensions when you can use an equality constraint or something like that.
Yeah, I think all of those are great points. You know, Alan was speeding up the workflow. One caution I will say with speeding up the workflow is when you are training, make sure to train in the most basic way possible at the beginning. So don't skip ahead and use quick mouse gestures if you are the training leader, because otherwise you're going to lose people. Like I have to install a keylogger on my machine so that people see where I'm clicking. I have to be very deliberate and slow. So sometimes those training sessions, at least to me, feel like a slog because it's so incremental and you have to check with all your people at every little step to make sure, hey, is your sketch actually fully defined or are you just claiming it's fully defined and stuff like that. So I will say that's one caution. Love the point about, making sure your sketches are nice, easy, neat, configurable. I think that's a huge thing that really helps teams get to that next level of CAD, but it's not taught as often. And a lot of new designers have trouble getting to that standard, I'll at least say, yeah. So great points there. Okay, here's a question from the chat. Cynthia asks, my team has no veteran designers, no training program yet, and not that much experience in CAD. How could we learn to CAD? I'd say, I think I'll speak for the panel here based on the resources we've discussed previously. And then anyone who wants to jump in, we can do that. And then we'll cover a couple more questions and we'll end for the day. So Cynthia, I'd say one, take a look at Chief Delphi, see what resources are there. If you're using SolidWorks, I'd like to plug my team's resources that were in the chat earlier and can be found on our website. But really there's tons of different places where you can find resources. Making sure that first, your most veteran CADer is comfortable with the resource that you are using to CAD. That's really important because if you just say, hey team, go look at this resource and learn to CAD, that can be an issue if someone gets stuck and then no one can help them. And also I'd say fostering a culture where your team is comfortable saying, hey, I have a problem, can someone help me figure it out? That's a huge deal. And it's a huge problem that I've noticed when I'm training. People don't tell you if, at least for guided lessons, if the screen does not look like yours, or if they found an error that didn't come up on your computer. And so I think fostering a culture of inclusion and really promoting that people should ask questions and correct you well, I guess not correct you, but say, hey, there's a problem here that I have. Can you please show me? A lot of people probably have that question. And I know it sounds like cliche because teachers say this all the time, but yeah, making sure people ask questions is a huge part of CAD training. I think at least because SolidWorks, or well, at least for SolidWorks, but really for all CAD programs. But these programs are complex and they have tons of things. And most people at FRC will never even touch half the features that your programs have to offer. So if there is something that is, niche that pops up and that maybe even the CAD trainer didn't know about, working through that together as a team and promoting that culture of being able to ask questions and get a response and make sure everyone's on the same page. That's really important. But back to more like resources, Onshape has a bunch of great tutorials made by FRC teams. I don't remember the number. It's like in the 2000s. I think the guy's name is Nick who makes them. Then SolidWorks has built-in tutorials. There are also a couple of, again for SolidWorks, because I know that they're in the virtual kit of parts, there are some professional training programs that come with that in addition to SolidWorks' built-in tutorials. I think Solid Professor is one of them, and I think DriveWorks as well. I have not personally used them, at least my team hasn't. If anyone else has experience with those, you can feel free to chime in after. But those are also resources. So yeah, finding a balance between whatever you can find from other FRC teams, professional tutorials. I think you'll be able to find stuff. It's not like the world of CAD is devoid of knowledge, and even a quick Google search can help you find pretty much anything. Most CAD programs also have like a help button if you're trying to figure out how to do one thing. Like I encourage my teammates to use the SolidWorks help tool all the time if they are like, I know that there's a way to do this, but I can't figure it out. That's really helpful. So hopefully that answers your question. If anyone has anything else to add on finding resources for CAD training, feel free to chime in and then we'll move on to the next question if no one else has anything to say.
Yeah, I have one resource. So when our team first started doing CAD back in 2014, one of our student then now alumni mentor, he watched a lot of videos from the Gray Bots, which is 973's, they call it RAMP. And that's a sort of video tutorial series on SolidWorks that shows how to make a West Coast drivetrain. Now, of course, some of the hardware has been updated, like the bearing blocks, of course, they don't sell anymore, but stuff from that series, a lot of it can transfer very easily. And that's a really good resource when you're first starting CAD. I know when we first started, we really liked those videos, so yeah.
Yes, and also for SolidWorks, SimBots 11.14, they have good SolidWorks tutorials as well. Yeah, I'd say they have a pretty good workflow. There were a couple things I didn't like specifically, but by and large, for most teams, at least for starting, they're a really great resource as well. Same thing with Greybots 973, I believe. They have, I think, a really great drive-based tutorial, if I'm recalling correctly, and some other stuff as well. Those are, I think, a little more advanced in terms of you need to have a little bit of experience already with that stuff, and you have to know where to source parts for them sometimes. But yeah, those are great resources as well. So thank you for pointing to that, Eli. Okay, we got 2 more short questions as well, and then we'll go ahead and end. So one of them is, how does your team teach standards and best practices for your team's CAD style? For our team, we try to bake it into basic CAD as much as we can, at least for like drawing standards and whatnot. And also like hole sizes and stuff. We teach that in our sketching and our extrusion lessons when we do guided practice. And then a huge part of integrating like our standards into the rest of our training comes with the intermediate stuff, where we teach how to use the SolidWorks library that we have, or our common parts library is another word for it, as Eli was using earlier. And so we do a lot of things in our more intermediate stuff after we know people want a CAD for FIRST. And so, yeah, we talk about like our precision and everything, and how to use our common parts library and our templates. And I love naming schemes, so I really like having an organized CAD system. So we go over our naming system there as well, so we can keep our parts organized. I think that's something that teams should definitely look into, just having a really simple one, like mechanism abbreviation dash part number, so you have a standard number. And then I like to add on a short description of the part in my naming system as well. So, okay. Eli, anything to add?
Yeah, so especially after our 2020 season, we really tried to make this a big focus of our CAD training. And basically, when we're doing our training, it's very similar to the way the Robot Dolphins do, but we always integrate stuff. And when we see students make the mistake the first time, like using a dimension that's not a standard measurement, we'll point it out so people don't get used to doing it a certain way. So it's really about catching it early and making sure people understand the practice we have before they get used to doing it a way that's not the right way for our team's standards. And basically from there, when it comes to SolidWorks, I gotta say the biggest one is just not using standard dimensions. And that's a big one you always want to look out for, because I can say many times and many wasted parts will cut something because, and then we'll have to recut it because someone didn't put the right dimension or something like that. And then another one is really make sure students know how to use your common parts library, and make sure they know how to use your CAD sharing software like GrabCAD, and you're not uploading over someone else's work, or you're communicating well with other members. And that's another big one. So really, if you just focus on those 2 things, you'll run a lot smoother. And I got to say, our 2020 season, we definitely would have liked to have a little more standards. So that's what we're focusing on now.
And yeah, so for Code Orange, at least, it's we also like to focus on standard. At least we focus on standards kind of in the demos. So when I'm kind of making a demo, and this is usually pretty much every single CAD training meeting, I usually give a demo, and I usually try and point out like parts of our standards. So like in like a sketch, for example, I usually point out when I'm like about to transition from the sketch to like a 3D like extrusion, I want to point out, oh, all my lines are defined here, everything's dimensioned, and I can't drag it around, because that's a big that was a big issue a couple of times. And and also I think Kyle mentioned the naming system. So yeah, we also love to have a naming system, makes everything organized. So we try and put that the first day in the first day intro presentation, naming system.
This ties into what we were talking about earlier. Many of the standards the team imposes on others comes from making their sketches and features modifiable and adjustable, as well as properly constraining sketches, as Alan said. We also have people explain their part in detail to talk about how it fulfills the goal and meets the standards and is modifiable and modular. And since a lot of the CAD is under supervision, we're trying to correct the bad habits before they start to take root in something that people do.
Okay, great. So this is going to be our last question. It's a little more open-ended, just as a nice closer. And I will say that our team did kind of steal Code Orange's naming system just a little bit. So props to them on having a great one already. And thank you, Alan, for echoing the importance of having an organized CAD system. But our last question here is specific advice for people looking to teach CAD. We've kind of looked at the principles and the workflow behind it that our teams have, but what is your best advice for people looking to teach it? For me, I'd say know that you're going to need to go slow and backtrack and be ready for people to have issues that they aren't going to speak up about. As I mentioned, you want to promote people asking questions, but it's not going to happen all the time. So making sure that we are just, making sure that you are making sure everyone is coming along with you and you're not leaving someone behind inadvertently, either because they're not asking questions or are misunderstanding something. So backtracking is really important. And also I just say, especially for teaching virtually, get a keylogger software. I'll put one in the chat in a second before we end, but get a keylogger so that people can see where you're clicking on screen that like highlights your mouse clicks and your scrolls and everything. And when you're holding shift and control and all that. So that's my really good, UI advice for that part. Okay, off to Eli.
Yeah, so one thing I always like to keep in mind, back when I was a freshman, I guess it's 4 years ago now, I always think about what was confusing when I was first learning. So again, just like what Kyle said, keep it real slow and always answer people's questions. One thing on the Super Nerds we always really like to do is if we're teaching a group and there's one student in that group who picks it up really quick, is we'll have them demonstrate it to the rest of the students who may still be confused. And that way it kind of forms a good connection with the student and the other people they're teaching, so then they know to ask questions in the future. And another thing I was going to say was really keep the stuff you're doing basic and don't just throw out a really hard project immediately. And another thing too is we used to always give out the laptops and have the people play around with CAD the first day, which can be good if someone doesn't get overwhelmed by it. But opening up the software for the first time, there's so many buttons and that can be a little bit intimidating. So it's always good to have them make a part with someone when they first start, and then from there maybe play around with them when they get home. But always give them a little guidance at the beginning, because it is a big software and it can be scary when you first start.
My piece of advice would probably be thinking from your student's perspective. So I think if you're teaching CAD, you've probably had a ton of experience in SolidWorks already, and that's kind of been doing SolidWorks for 4 years now. So I always keep on forgetting like the basics of SolidWorks. So I have like mouse gestures and like a bunch of keyboard shortcuts, and when I'm giving my demos or something, I always accidentally hit those and I don't have a keylogger. So I only have my mouse highlighted sometimes. And then, so everyone's always confused because they're like, always like, hey, how'd you get that feature? How'd you pull that feature out of thin air? And as well, like my SolidWorks has a lot of different customizations on it. I run dark theme, so it always looks different than the students' SolidWorks. So it's kind of like a bridge that you have to like cross. So yeah, just think from, if you're brand new to CAD, think from their perspective, because sometimes you get a little bit too, sometimes if you're teaching CAD, you're already a bit too acquainted with SolidWorks.
All right, and I'd say there are three main ones. First is to understand that they will, first of all, have encounter problems and understand what you're doing, and understand that the problems they have won't be specific to the problems that you first had while learning CAD. Second, we try to definitively enforce a way of modeling the part, assuming that they do it in a way that is intuitive, modular, easily adjustable, and meets your criteria. And also make sure that the group of students who will be working with each other for FRC and in general will understand to work together. So give them group projects, give them ways to encourage collaboration.
Okay, and with that last answer, that's a wrap on our first panel of the 2021 Summer Series. Thank you to all our panelists for sharing all this valuable information. We really hope that it was helpful in maybe having you consider a different approach to your CAD training and looking closer at your CAD workflow. And we hope that even though most of us use SolidWorks, you're able to apply this to other programs as well. Again, we really did want to focus on the principles rather than specifics. So with that, thank you all for watching today. We'll be back tomorrow with day 3, and the workshops we have are, again, with 3476, we have advanced scouting methods, including API scouting and making a pick list. And then we have an amazing panel coming up as well at 5:50 p.m. on Wednesday, and that is the Shop Essential panel, which is going from starting with your first $10,000 or your first $100,000, or not 100,000, sorry, first $1,000 or your first $10,000 to your next grade expansion. And that's going to be with a lot of experienced mentors and a couple experienced students, including a guest appearance from Team 3309, the Firebots. So we're excited to see them there as well. So we hope to see you tomorrow, and thank you all for watching again. Bye.